All right, today we're doing section 4.6. So first, let's look at the book. We already scanned this page, so I'm just going to maybe zoom in this part right here. Yeah, that should be good enough. And next, page 142 and 43. Let's see. Okay, that's zoomed in. That should be good enough. Kind of tilted. Let's see, maybe I turn it this way. Okay, and then zoom in a bit closer on top. That corner seems, why does that corner look? Okay, and then the bottom. Let's see, what am I doing wrong here? Okay. All right, and then page 140 something. What is that? 44 and 45. All right, and then zoom in a bit on top. And then a bit on the bottom. Let's see. Okay. So let's start on section 4.6, and let's talk about a family of plane curves. A family of curves just means a bunch of curves that is somehow connected with some kind of a variable. For example, let's consider a family that's called f(x), y, and alpha. Okay, equal to 0, where alpha is the determining constant that determines which member of the family are we talking about. As an example of that, let's consider, for example, you have a unit circle, let's say, okay, and the unit circle, each point of the unit circle has a tangent line, right? Here's one tangent line, which then all the tangent lines around the unit circle can be considered as a family of these curves that we're talking about. And then right, so that is well, first let's calculate one particular tangent line, and the equation of any specific tangent line that makes the angle, where the angle down here is alpha, okay, would be, if you work it out, please work this out yourself, it would be something like this. Okay, after you do some do something, and remember that the slope multiplied to m1 with m2 is equal to -1 for perpendicular lines. Anyway, you will very quickly come up with this equation for any line that is tangent on the unit circle. It depends on the alpha, which is the angle that the normal makes. And like I see a picture here. So then this particular equation right here is the family. Okay, if you set f equal to this thing, then the f(x, y) alpha would be will represent the pack of family. Well, when everything equal to 0. Okay, so and where you just subtracted. That is, we have this equation, of course, -1 equal to 0. Set that as f. That will be the family that is the tangent line, the family of tangent lines of the unit circle. And so that, which changes according to alpha. See, if you define alpha as the angle where the tangent line makes with the x-axis, with the positive x-axis. So alpha can increase from 0 all the way to 2 pi. So then, so that's that. Now that would be one some quick example of a tangent line, of a family of curves that we're concerned with right now. And you can see how you can describe the entire family with a formula like this. Okay, f of x, y, alpha equal to 0, or this will be another way of, or this thing equal to 1. Now the next concept we need to mention is something called the envelope, and towards the bottom of the page. What's the envelope? The envelope is a curve that's touched by all members of the family. And well, in our example of the unit circle is definitely the envelope of its tangent lines, okay, just by its own very definition. It touches all the tangent lines, of course, and therefore the unit circle is the envelope of the collection of tangent lines that we just mentioned. In general, right here, please notice this sentence right here. Any curve is the envelope of all its tangents. Again, that seems like a fairly obvious fact. Okay, and I'll show you another example of an envelope, just some random example. As you can see, there is, let's see, yeah. So my curve, I have a bunch of lines, right? But they all tangent to this blue curve, which is y squared equal to 4x. Yeah, it just, well, I drew a bunch of tangents to it, and as you can see that any curve is the envelope of its own collection of tangents. Okay, so that's that. Now, now let's move on to the bottom of the page, section 6.1, definition 3. We're going to define envelope exactly, okay? Which doesn't sound that different from what we just said, which is if we define an envelope, which is a curve, right? A curve that has a bunch of, that is tangent to a bunch of stuff. So if we define it parametrically, so that x is g alpha, y is h alpha, then at each point of alpha, then the point g alpha h alpha of curve 3 of this curve that we're talking about lies on the curve lies on the family of curves, okay? That is, they share, each point of the envelope shares a point with somebody in that family of curves, that big collection of tangents, but it doesn't have to be tangents. It might not be a straight line. It might be some kind of curve. So the family is f x y alpha, and our specific envelope curve is each point there is touching some family member of that collection of curves, and they have the same tangent there. That is, they don't intersect, they only touch, so that way they both have the same tangent, which is an interesting concept that we are developing here. So let's look at the next page. We're on page 142. It describes example A, which is repeating what we just said, okay, that the unit circle is the envelope of all its tangents going all the way around. And so please read this example yourself. It gives a little more detail of how to find the slope and stuff, and all of which I think are pretty straightforward that you can figure out very quickly. So please read example A yourself, and we'll move on to theorem 6. Theorem 6 says, now we have 5 conditions in theorem 6. Okay. Now first, the function f, we have the family. Okay, and we have a family of stuff. Let's imagine for this as an example, let's think about all the tangent lines around the unit circle as f, okay? And then we have g alpha, h alpha together defines the unit circle, okay? That is sort of like this. Here's g alpha and that's h alpha. So we have these two things define some kind of a curve, whereas f is an entire family of stuff. And then we have certain conditions about the partial derivatives that's not zero, so that things don't collapse on us. And then next we have, and then the 2 points are touching, okay? So f of, if we plug g into f, then a equal to 0. That is, everything fits. And then here's an interesting point that's different. There's f3, that is the function f, once you plugged it in, okay? If you take the partial derivative with respect to alpha, it is identically 0. Now, if this is true, if these conditions are true, then the family, that is f, okay, equal to 0 is the family, has a curve which is g alpha h alpha as an envelope. So then that's how you can determine the two things are envelopes. And that is the theorem. Now, first let's prove the theorem, okay? Now, we know that, of course, the points has to touch, right? So for each alpha, the point G alpha H alpha lies on the curve F, that's already given because when you plug it in, E equal to 0. So they are they share a common point. Now, so then the question is. Now, let's just look at this, all right? Now, we have f, x, y, alpha equal to 0, and it has the envelope, okay? And then, so let's pretend y is a function of x, so, and plug it in here. And then, so y is dependent on x. Let's take the partial derivative of f with respect to x, and then this is what we've done many times before. We get quickly that dy by dx is negative f1 over f2. In this case, we assume f2 is not 0. And then next, what we're gonna do is plug g and h in here and take derivative with respect to alpha, because we need to calculate f3, and we do that, we get this pile of stuff, okay? And then, well, we are assuming that f3 equal to 0, so then this is already disappears, so we just have these two things left, which equal to 0, as given by condition 5, okay? The partial alpha of this stuff equal to 0. So then if you look at these two things, it looks similar to that, specifically dy by dx, which is that, right? Which from this equation equals to this. And therefore, h prime over g prime is the slope of this point. It's identical to dy by dx, which means whereas h prime over g prime is the slope of the parametric equation. See, as a result, then we have therefore this the x equal to g alpha, y equal to h alpha is the envelope of f. Okay, that is the conclusion of the proof. Please do this yourself as well. Well, anyway, yeah, so please do this. This looks dark. Does it look dark to you? I guess it's fine. So please do this yourself as well to work out the details of how that comes about. And then, of course, sometimes it might be something might be infinity, and if it's infinity, that just means that some line is vertical, and that works out just fine as well. Okay, if that is, yeah, if g prime equal to 0, then let's see, right? So either way, the point is that we have so that being that they have the same slope, that means they're tangent at the point of intersection, and therefore by definition that is the envelope. Now, both slopes, well, at times if something is denominator as 0, then the other one denominator is 0 as well. It just means that both have in a vertical slope is all that means. See, I have it written right here. If f2 is 0, then g is 0 as well, and everything's infinite, and vice versa, like if this applies to f1. Anyway, so that is that. Okay. Now next, let's so please prove this theorem yourself as well, okay? And then we'll move on to the next concept, is that the theorem provides an interesting way, interesting but simple way to determine the function that f and h. That is, if you have a family of curves, right, and you need to find its envelope, then what you do is you simply follow what you're going to do is you have the f equal to 0. You're going to take the partial derivative with respect the third one. Okay, that is, you follow this principle right here, and then so now you have two equations, and if you solve them, and so that you come up with x and y equal to something, then that will give you the envelope. Okay, those two equations together defines the envelope. Okay, and so here's if you apply this trick to example A, that is that circle that we've been talking about up here, you will quickly notice these two to be true. So please confirm that yourself. You can do that by just staring at this thing for a few moments. And you notice quickly that that is the f, okay, and this is f3, and you notice, and everything works out very quickly. So the solution is, because the solution is exactly of these two simultaneous equations down here, is exactly this thing, okay? And that, if you stare at it, you will figure that out. Now, so that is that. Then let's look at the next page. There are a few comments about the theorem 6. That is, a lot of the conditions are actually overkill. We don't even need it that much. For example, if you we can come up with examples that doesn't satisfy even the first condition where f equal to c1. Okay, this thing doesn't exactly belong to c1, but that's okay. It still works for as an this things you can still come up with an envelope for it. Now, specifically, what is this thing? Now, if you are to plot this thing out, okay, x plus alpha equal to the square root of y, if you plot it out, it looks something like that. It depends on where alpha is, and it's half a parabola. And then depending on alpha, it slides along the x-axis, and therefore, it touches the x-axis as a tangent, so x-axis is its envelope. However, we can't use the theorem for various reasons. For one thing, the function f is not as defined. It doesn't belong to C1, so it doesn't fit there. And then more importantly, f3 is 1 all the time, okay? The f3, which is partial f partial alpha, is exactly 1, but our requirement is the f3 equal to 0, right? So we can't use it, and there's more than one reason that we can't use it, and yet this thing clearly has an envelope, and it does just fine. Now, however, the entire parabola is translated. So now if we redefine the function to be the whole parabola, in other words, the function, as we call it this thing, okay, that is the entire parabola instead of this is half of one. If we define it as the whole thing without the square root, then everything looks okay. And then, because if you were to take the partial derivative and you quickly work these two things out and realize that the x-axis is again y will be 0, therefore the x-axis is its envelope. Okay, so so please work out those little details yourself. It's pretty neat, you know, how we can come up with envelopes of various things. So next, let's look at example B, where we need to find the envelope of the family of lines and the sum of squares of whose intercepts are unity. That is 1. The family has equations. All right, so let's consider a family of lines. That means straight lines, okay? The intercept formula from algebra says x over a and plus y over b equal to 1, where a, b are the x and y intercepts. You can see that if you set y equal to 0 or x equal to 0 very quickly, why that would be the intercepts. And it says the sum of the squares of the intercepts is 1, so it's right here. And then we are going to simply apply this thing right here, okay? We'll have a function f(a)xy alpha, and then take the f3. Now, being that this function is here's f, okay? It has two variables, but we'll take one, plug one out to represent the other, okay? So in this case, that way alpha we'll set alpha to be a. So alpha is chosen as a, and then there's a way to represent b, right? But we're not going to do the square root because because the square root only shows you half the answer. So instead, we are going to let b be a function of a. That is, we're going to calculate everything implicitly. That way, we don't have to worry about the square roots and stuff. So then f of x, y alpha now becomes f of x, y a, which was alpha as a, okay, which equals x over a and y over b as a function of a minus 1 equal to 0. And so let's take the partial derivative of f3. And to do that, we also need to know what dB by dA is. That is, what is b prime? And from this equation, okay, then b prime we can quickly calculate equal to minus a over b. And then with that, we plug it into the f3, which has b prime in there. And then after some mess, then we get this thing. And so, yeah, and then continuing, if we then we need to solve these two equations, F3 and F1. Where's F1? Right here, okay? Because these two simultaneously being solved, after some algebra, we have, let's see, you plug it in there, right? And then eventually, here's what I got, x equal to a cubed, because a squared plus b squared is 1, as we are given in the beginning. So y is equal to b cubed. So then we get some kind of relationship. Eventually, we figure out that x, being the a squared plus b squared is 1, then we get this final solution. So it's a bit of algebra. It's not bad. So please do this yourself, okay, to confirm that example B works out by applying equation 6 on page 142. It's just a straightforward application. You take the function, and then you take the derivative with respect to alpha, and then just solve the thing. And one way or the other, okay, is going to come out. So basically this whole section is about this equation right here. Let's get the equation 6 to come out. And come out with these two equations, and then solve the simultaneous equation, and you're good. So please do that. And example B, and we'll move on to section 6.2. 6.2, we are going to prove that a curve is an envelope of its tangents. Now, if you look at the previous page, page 141, you notice that I have it marked right here, a silver dot, where it says any curve is the envelope of all its tangents. Why? Because that's obvious, right? But now we're going to prove the obvious point with what we just learned. So we'll use this equation 6 and prove the fact that any curve is an envelope of its tangent. So to do that, then we'll just slap this thing on there, okay? We have a curve, right, y equal to f of x, and then the family of its tangent is this thing, which you can work out very quickly, is something that you've done many times during math. But do this again, and you can work out a tangent of any curve is this thing, okay, at a point alpha. All right, so you can see the family of tangents looks like the function, the family function, and then we need to calculate the envelope, right? So we apply equation 6, and I have it all done right here, I believe. Yep, I hope so. All right, right. So here's the function. The family of tangents is right here, okay? And then G3 is this thing. Actually, let me see. Yeah, I should mention that the reason this is G3 is because normally we would call it F3 to follow equation 6 on page 142, but this function is already called F, so I call the family G instead. I said it right here, okay? And then, so there's the family of tangents, and we came up with this equation remembering the good old point slope formula, right? And so there's the pack of tangents for any function y equal to f of x. So let's call the tangents G, the tangent family G. So then we calculate G3 by formulas by equation 6. So G3 equal to that stuff, and eventually you get some G3 just equal to this, okay? And then if assuming that f double prime is not 0, and so that it's not a straight line, right? And because that is the assumption of this. Well, let's not worry about f double prime equal to 0, so we can get rid of that, which means x equal to alpha. If x equal to alpha, plug it in here, then y equal to f of x is indeed the y equal to f of x is indeed the envelope of that family that we came up with, which is this is just. So we're trying to use theorem 6 to prove what we already know, that any curve is the envelope of its own collection of tangents. Okay, so next we are going to talk about something called the evolute. Let's pronounce, I don't know, I'll call it evolute. Okay, evolute, what's an evolute? And well, an evolute is, first let's see what it is. The word evolute means is defined as the locus of the centers of the curvature, okay? I don't remember talking about evolute in Calculus 3, but whatever, okay? It's just the path. If you connect all the points of center of curvature, you get this curve that you give it a name. It's called evolute. Okay, so but what are we doing now? What we're doing right now is we're going to consider the normals. That is the normal to curve 10. So what is curve 10 again? The curve 10 is just any old curve, okay? Y equal to f of x in C1. So given some curve, now we just finished working on its tangent, but now we're going to do the normals, okay? So what is the normal of some random curve? And that we have the normal of some random curve is given, again, using the point slope formula. You can quickly come up with, remember the tangent is f prime, so the normal slope is -1 over f prime, right? Because there's that rule from algebra. The two slopes, the perpendicular slopes has to multiply to be -1. And the reason I remember this is because I just did that recently in algebra. And so there's this. So we have the normal equation, which you rewrite it to look something like that, which we will again call it g instead of f, okay, gxy alpha. So then calculate g3, and after some messing around, and don't mess up anything, I think I messed something up here, but eventually I got to here. This is g3, I guess. I think let's see, what did I do? Yeah, I think g3 equal to 0, so I dug y out of there. So I got y, and from y, then I was able to dig x out, right? Is this x? Well, x, what? X, yeah, well, anyway, the point is you can dig y and x out of these things from the equation, from equation g, okay, and g3. So let's dig that out. And then, so we have x and y, and that is about it. That is, you have these. So x and y looks complicated, okay? That is, but your book says this is exactly, it just happens that x and y represented this way is the locus or the path of the center of curvature of the curve. Okay, that. So then the normal to the curve is then tangent to the evolute. Okay, so that is and that's all we're going to say about that. Okay, and we have come to the end of this section. It's a pretty short section, I think. So let's do some homework. For homework on page 144, please do problems 1, 3, 5, 6, 7, 11, and 12. And most of the homework, and let me just tell you that right now, has to do with solving this equation. Okay, just like equation 6. So pay attention to the equation 6, and you just plug everything into that, and you'll be all done. All right, let's look at problem 1, which is, I think, quite straightforward and not much trick to it. Let me show you where did I do that. I just need to find it. Okay. Problem 1 is, problem 1 is very short. See, it's just down here. This is about it. We figure out what f is, calculate f3, and then solve them together to get y equal to something and x equal to something else. And then we notice that it ends up being y squared equals to 4x, and that is the envelope of this thing. And then I have it plotted here, right? Yeah, suppose I plot this thing, and nowadays we have the calculator to do the plotting, which makes life much better. As you can see, this is y squared equal to 4x. I showed you this earlier as an example, but this is problem 1. And you type in all the lines, and then and you notice all the lines are tangent to the envelope like it's supposed to. Nice. Well, that is that. Next, let's look at problem 3. Problem 3 says, let's see, problem 3 says that, where is it? Never mind. Problem 3 is a similar thing, right? The sum of the intercepts is constant, all right? Sum of intercepts, well, first let me find it. problem, okay, here it is. The sum of the intercepts is constant. So we have this thing where the sum of the intercepts function. So we have function f, okay, and then f3, which we use alpha as a in this case, where c is just some constant number. And once we get that, we solve these two equations together. After some stuff I did, I eventually got right here, y equals to that, and x equal to that. Okay, and that makes sense. It's symmetrical. As you notice, c minus a is just b, right? So y is b squared over c, and x is a squared over c. So the answer is symmetrical. And then eventually we get, so that's the parametric representation. And you can also get the direct representation after taking the square root or something, and x equal to this as well. So I also plotted this thing out. You're supposed to plot a bunch of lines to show this thing. Okay, so I did that as well, which is problem 3 right here. Okay, and you can see it's similar to the one before, except that now our curve is, I graphed this thing. Can you see it? Okay. Anyway, yeah. See, the equation, I graphed it down here. It seems fuzzy. Why is it so fuzzy? Let me see if it gets better this way. That's a T there. It still seems not very clear. Okay, that should be clear enough. Okay, so it's a bunch of T anyway, so we graphed it like this, and then everything's looking great. Right. Well, anyways, that's enough of staring at the graph. So that's problem 3. And next, let's look at problem 5. What? What did we do? Yeah, a plus b is c. Oh, this time a times b is c. Okay, all right, which is fine. So a times b is c changes nothing. Here it is. We have function f, right? Function f3. Solving the two things together, we get something about x is a over 2 and y is c over 2a, or x times y equals to some constant. Being that it says the area is constant, so we don't care if something is positive or negative. That's why we slap on a absolute value there to take care of that small detail, being the area being constant. So that's that. Okay, problem 6. We're trying to show that the parametric representation of a curve is still the envelope of its tangent. And okay, so let's do that. So and let's dig out the parametric representation. Okay, which has its calculate its tangent and then the equation of the tangent, which then we will represent as fx and fxy and alpha, and then take the f3. And then solve these two things together, which then you notice there's a ton of alphas in here. So I stopped writing alpha in the next line, which make things look a bit clearer. And equal to 0, and then I think that is the f, and this is the f3 equation. Well, from the two things, eventually I got y minus h equal to this thing. Okay, equals to that, which then, if we assume that these two values are not the same, that would mean that x has to equal to g, and y has to equal to h, which is the envelope. As yeah, right here, see? X and g, y equal to h is its own curve. So then the parametric curve is the envelope of its own tangents as well. So that's problem 6. Did I show this to you properly? Okay, that's clear enough. And so next, problem 7. Problem 7, we have, what is that? Oh, I think now we're calculating the normal of the parametric curve. The same thing we did in problem 6, except that the answer now is going to look a lot worse. So the normal, calculate the normal of the parametric curve, which is that thing, okay? And then which give us f, and then we calculate f3, and then we need to somehow, dig ourselves out of these two equations, dig x and y out. So then after some manipulation, I was able to get everything to come out correctly. Now, it's problem 7 has an answer at the back of the book, and this does check out. They don't look exactly the same, I think, but they do check out if you look at them closely. So, so this is correct. So that's problem 7. Next, let's do problem 11. It says find the envelope of family of spheres. But we have not said anything about spheres, okay? So far, we've only talked about envelopes of curves. But we're just going to go ahead and do it like it is a curve anyway, okay? And apply the same trick that we've been using. So then the family of... so we'll say f x, y, z, beta is equal to, you know, the beta and stuff. And then we'll take the derivative with respect to beta, okay, just like the way we do with alpha. And just crank the whole thing out like we've been doing, okay, without having proven that this even works. And how do I know that my answer is going to be right? I will show you in a second. Anyway, so we crank this thing out. So then we solve these two equations, which gives us something. What does it give us? It gives us some envelope. Okay, this is the envelope of this thing if everything works out like it's supposed to. Yeah, after I did these two equations, x a and well, whatever. Yeah, I can't read the details yourself. The point is, after messing with the algebra, I came up with this thing right here. And then, what are the, let's see, what are the spheres? Yeah, there's the spheres. And anyway, I calculated the envelope, okay, by plugging, because I was able to calculate what B is in terms of x, y, z, which is right here, and then plugged it into the original equation. And I'll choose A to be 0. Okay, and then we have this pack of stuff as the envelope of the original function f right here. Now I was thinking, how do I know this even works? Because we've never even worked on the sphere situation, only curves. Well, I plotted this into the 3D calculator, and as you can see, it does work. There's a bunch of spheres. Oops. There's a bunch of spheres, right? And then this, the red thing down here, is the envelope, okay? And as you can see, the spheres all line up into an interesting clump, and then the envelope does wrap it like an envelope. In the 3D situation, in the sphere situation, it wrapped it all the way around. Yeah, isn't that nice? So I know that the equation 6 or theorem 6 does work, at least in this case, okay? Because things worked out. Look at that. You can't get any more envelope than this. It's wrapped really tight. It's all tangent clear around every single sphere. See? So yeah. So that is, as you can see, that I typed. As you can see, you can type in a sphere in there by just typing in the equation. See, like that. And then it's a very Desmos. This is in Desmos 3D, of course. Yeah. So that's that, and that's problem 11. And next, let's look at problem 12. Problem 12 is, where is it? Oh, here it is. Now, problem 12, we have two variables, okay? Again, we have not done that in this section, but we're just going to blindly charge forward anyway. Well, but what do we do with two variables? Then we take two derivatives, okay? Here's the original function, which I copied down there. We take the derivative with respect to alpha, and then with respect to beta, and which give us some stuff, okay? And then we'll solve for alpha and beta and plug it into the original equation, which gives us, after cleaning it up a little bit, we got this thing right here. All right, and then, so does this work? So I plotted everything into the Desmos 3D calculator and find out that it does indeed work. As soon as I find that thing. Problem 12, okay? And come on, get out. There we go. And so here is problem 12. Now, let me blow this thing up so you can see it better. Now, the problem 12, as you can see, here's my pack of equations where I choose beta and alpha as different values, okay? And you can see this odd looking thing. If you plot it yourself, you'll be able to see it better. But the point is that it has a bunch of spheres, and you can see each sphere here. Okay, I only show the sphere. I show the sphere with part of it missing. A lot of the spheres have part of it missing, so that you can see inside. And anyway, the spheres, as you can see, is yeah, each sphere you can see part of it. That is, if you turn each sphere on and off by clicking this button here, okay, these buttons, then they'll turn on and off. Then you notice them in here. Okay, they're all in there somewhere. From this angle, you can see each sphere. I think I plotted 12 of them or something in here. And it doesn't, yeah, I have 12 spheres. I said right here. There are 12 spheres that I plotted. And as you can see, they all look pretty decent. And then, yeah, and let's see. Anyway, so that's that. And finally, this is the envelope, okay? And when you slap the envelope on there, this is what it looks like. I mean, look at that. The envelope actually touches every single sphere in 2 spots, okay? Every single one. And the spheres are, as you can see, the spheres are in a big clump. But if you look at individual spheres with the envelope, you notice that every single sphere touches the envelope. Okay, that is, the envelope does work. And look at that, it's wrapping this thing up, and as you plot more and more spheres, then the thing the envelope is just stuffed full of spheres, all the way up, down, everywhere. Yeah, well, the spheres are empty on the inside, of course. So anyway, that is now, isn't this cool? So please plot this yourself if you can. If you have access to Desmos 3D, which is free, but I don't know, who knows? Maybe it's not available in some places. Who knows? I hope that's not the case. Let's see. So problem 12, I should also mention that something is, yeah, alpha and beta should probably be bigger than or equal to 0, because the way the sphere is designed, okay, alpha and beta is their radius. So if it's less than 0, your sphere is going to have a negative radius and it won't plot. So choose alpha and beta to be bigger than 0 and equal to 0, and then you got a big pack of spheres that's looking very nice. And that should mark the end of this section. Oh, I forgot to say that the author of this book, that this book is designed in 1947, is they probably never imagined that some 80 years later that we are able to plot this thing. Okay, because back then, without a 3D calculator, later graphing calculator, how are you going to be able to see what any of this means? But then they can sort of imagine it, okay? But this is so much nicer. See, we live in a much better stage for learning math in terms of calculators, that we can see a lot of the stuff. I mean, look how cool this is, okay? I just can't get over how nice this stuff looks.